There's an equilibrium involved in the formation of a solution. So we're going to look at putting sodium chloride in water. So in this beaker, we have a lump of sodium chloride sitting in the bottom of the beaker. And when this first happens, we drop that crystal in there. The only thing that can happen is that the sodium and the chloride ions will begin to dissolve into the water. And they will do that as the water molecules come and form ion-dipole interactions. And so here we see that happening. The water molecules are surrounding them and kind of escorting them out into solution. So as that happens, now the solution becomes more concentrated. There are more sodium and chloride ions out there. The reverse reaction can also happen, that sodium and chloride ions can come together and redeposit, can recrystallize onto the sodium chloride crystal. And so now we've got the dissolving process going, and we also have the recrystallization process happening. I don't know where that sentence was going. Eventually, we can get to an equilibrium situation where we have the rate of dissolving equal to the rate of recrystallization. And I guess I should have been pointing around down here. Here in the middle, we have a little bit of recrystallization happening. That's going to be dependent on the concentration of sodium and chloride in the solution. Originally, none of that happened because there was no sodium and chloride to recrystallize. This dissolution keeps happening, but the recrystallization increases because the concentration of sodium and chloride out here in the solution increases, so this rate increases. Eventually, these two rates become equal, and you have sodium and chloride ions leaving the crystal and returning to the crystal. So it is similar to the evaporation process where we talked about molecules near the surface, if they have enough kinetic energy to break free. We talked about playing Red Rover, and they can break free to the gas state. In a closed container, they'll bounce around, and eventually they'll hit the surface of the water again and get trapped. So we get a dynamic equilibrium eventually where the forward reaction of the sodium chloride dissolving is equal to the rate of the recrystallization, the sodium ions and chloride ions reforming the sodium chloride solid. If we have a saturated solution, that is one in which the dissolved solute is in dynamic equilibrium with the solid solute. If you add more solute, it won't dissolve. It'll just go to the bottom. You've reached a maximum amount of solute in solution. An unsaturated solution, as the name implies, is not saturated. It has less than that equilibrium amount. And so if you put more solute in, it will dissolve. And you can keep adding solute until you reach that saturation point where the rate of dissolving is equal to the rate of recrystallization. And then there's the supersaturated solution, which contains more than the equilibrium amount of solute. Does that sound impossible? There is more solute dissolved than can dissolve at that temperature. That sounds impossible to me. The way these solutions arise is that the solubility of the solute is temperature dependent. And so you can make a saturated solution at an elevated temperature and let it cool down very, very slowly. It's a little bit like Bugs Bunny or somebody running off a cliff in the cartoons. If we did that, we'd fall the first step, right? But they don't fall till they notice that they ran off the cliff and they're in midair. Then they fall. So supersaturated solution is a little bit like Bugs Bunny right after he ran off the cliff. It's got more dissolved than will dissolve at that temperature. And it's not until somebody bumps it or drops a crystal into it that it precipitates out. And this is a picture. I've also got a cool video to show you. This is a supersaturated solution, and they're just going to touch the surface, and it begins to crystallize, and the whole thing will end up crystallizing. So these supersaturated solutions are unstable. Yes?
How is it even possible for it to have one of the...
Right, it seems completely impossible, right? As it has to cool down slowly, and it is definitely unstable. But as it cools down slowly, if there's no nucleation site, no little bit of the solid present, it just doesn't get started. It needs something to start, and then it goes like crazy.
Would shaking also be one of those?
Yeah, if you shook that, it would crystallize. Sometimes if you just bump it, that can happen. Definitely if you take a stirring rod and scratch the bottom of the beaker, that'll happen. Or you drop a crystal in, or sometimes even if you like just touch the surface, it'll start. And the reason we can do that is because the solubility is temperature dependent. They don't have sodium acetate on here, but sodium acetate is the one that makes awesome supersaturated solutions. But if we look at something like potassium nitrate, so at room temperature, which is about here, potassium nitrate has a solubility roughly of 35 grams of solute in 100 grams of water. When you increase the temperature, the solubility skyrockets. And for most of these solids, you see that it has a positive slope. It increases, right? Sodium chloride is is quite level. It's not real temperature dependent. But then we have sodium sulfate, which has the opposite. At higher temperatures, it's actually less soluble. But most of them, as you increase the temperature, you increase the solubility. So if you took a solution of, if you took 100 grams of water with potassium nitrate in it and took it up to 40 degrees Celsius, you could get 60 grams to dissolve. If you cool it back down, let's say you cool it down to 20 and the train doesn't come by and jiggle it, you might be able to form a supersaturated solution. Only 30 grams should be soluble at 20 degrees Celsius, but you dissolved 60 up here. Now that's not going to be stable, and some solutions, some solutes, it's pretty impossible to form a supersaturated solution. But if you bumped it, then half of it, 30 grams, would just suddenly precipitate out a solution. Recrystallization can be used to purify a solid. This is where you take a saturated solution at elevated temperature. So say you collected a precipitate, we've done that in lab. You collected a precipitate, and sometimes you get co-precipitates, and you don't want those, you want to get rid of them. Well, you can heat the solution up to get your product to dissolve. And then you let it cool slowly, and as it cools, the ions have more time to crystallize, and there's more opportunity for recrystallization and dissolving, and for that whole equilibrium to slowly develop. And what happens is the interactions between the ions in your product are going to be maximized if the crystal is pure. If you get other things in there, they're going to mess up the crystal structure, and that's going to be a higher energy. And so it will naturally exclude impurities as it crystallizes slowly from a saturated solution. And you can make rock candy by recrystallizing table sugar. I tried that at home once when I was a kid, and I'm sure I did it wrong because nothing ever happened.